Got to be careful here. Bears like to come through here. We're looking at the third part of the Fresnel diffraction physics as our course is coming rapidly to an end here. We're almost finished the semester. Fresnel diffraction, we're going to get involved here with looking at a infinite wall that takes up half of the plane and look at shadows and interesting things that happen at the edge when we look at the shadowed region. And then we're going to replace that with the moon and have a star far away, light grazing the limb of the moon, and do some neat stuff there. And then we'll look at the single slit with Fresnel diffraction and see some marvelous effects. Now, though these equations ultimately lead to integrals that are not done in the regular fashion, we use the Corneal Spiral and the Fresnel integral tables. They're a lot of fun. So I hope you enjoy our discussion of the Fresnel diffraction part 3, which brings the Fresnel diffraction section unit to a close. Chapter W, Fresnel diffraction 3. Let's talk briefly about the last class. Summary from last class. Now we have a sheet to do that. So what we did last class is considered an opening aperture, and this border here goes off to infinity. So there's your opening. Source point over here, and observing point over here, a screen, and then some parameters, rho naught, rho, and then R naught and R on the other side. And you then look at this point P and have a solution, a formula for the strength, the amplitude at point P, and then you integrate over the aperture. And here the coordinates are going to be X and Y, but then we're going to translate those into a U and a V. So that this direction, the X direction, is also a U direction, and this Y is also a V direction. So these are the equations that translate the variables, and it's easier to work with the U and the V variables. So things simplify a lot, because see, then up in here, this starts to look very nice. And this leads us to the Fresnel integrals that we looked at, and have the Corneal Spiral, say, to look at that. Fun thing to do is to just make this aperture larger and larger, so B goes to infinity, H goes to infinity, and we have no obstruction whatsoever. So if we do that, let me write down the formula that we had, because now we're going to calculate. We have A naught over 2, the master formula, and we're going to integrate here U1 to U2. This is the general formula. We're going to break this up into the 2 dimensions. Like if we had a rectangle, we would go length and width. Here's V1 to V2. So I'm just copying down the formula from the previous page. V squared over 2 dV. And now what I want to do is I want to integrate over everything. Like the aperture, this is see, you integrate over the aperture with these parameters, but there is no, the aperture now extends to infinity. So in that case, I'm going to have A naught over 2 go from minus infinity to plus infinity, e to the I pi u squared over 2 du. And I have the same integral here for the other dimension, e to the I pi v squared over 2 dv. Now, we know we have worked this problem out before when we had the Corneal spiral here, and we looked at, say, doing something like this and going out like that. So when you integrate here, this is minus infinity down in there, and this is your plus infinity is up in here, and you're looking at the plot here of the cosine u and then the sine integration. This is the Fresnel integrals. When you split this up, this will have the cosine of this plus I times the sine of that. So have those done, and then when you go from minus infinity to plus infinity, you really want to do this phasor here to go from there to there. And then you might recall this was minus a half, your coordinates of this, and up in here it's plus a half and plus a half. So that means this phasor, you can think of it as going over 1 unit along the real axis and 1 unit going up. So that means this integral is 1 plus I. That's it. That's how nice it is when you work with the Corneal spiral. And this over here is another 1 plus I. So then when you do your modulus, you have here A naught over 2, and then we have the 1 plus I and the 1 plus I. And I showed you earlier in the notes a little review of complex numbers and the modulus. You could break this up into the modulus of the first one times the modulus of the second one. And the modulus here, you can think of it as the length. And if you have a 1 there and a 1 there, it's a square root of 2. That's all it is. And this square root of 2. So the 2 square root of 2 is going to give you a 2, and that'll cancel the 2 there. And like that's what we expect, that this is a very beautiful calculation to show you that, to confirm that everything's working well, that if you have no obstacle and the aperture is an infinite and the opening's infinite, that you're seeing an unobstructed wave. So we call that the amplitude of the unobstructed wave, or the unobstructed source. And if you want the irradiance, that's going to be 1/2 A naught squared. All right, so that's a nice little review of things and show how everything fits together. Okay, so now we're going to go on to W1 and consider an edge. So, the first case we considered like no obstacle, but now we're going to have an obstacle that's going to be infinite, but half the plane. So here we have a nice little diagram to show you the geometry, the setup. So what we're going to do here is have this plane. This goes off to infinity at the top there. So this is a big door, blocks everything, blocks half the space. So we're going to then integrate over the aperture, which is going to be half of the plane. So we're going to integrate from 0 to infinity on the and going to go from negative infinity to plus infinity on the other dimension. All right, that's what we're going to do there. So let's set that up, and then check out this. Here's a nice little screen, and we're going to observe it from the other side, a translucent screen, so that the x is positive. You know, here's your little x. I'm using a big X, a capital X for the screen, little x. And when you're very, very far away, you know, this is going to be about the same. And we don't mean Fraunhofer far, but we mean like far enough compared to like sizes when we have slits and things. But for now, let's just go ahead and not worry about that. So here is the screen, and here's the point P, and we're going to integrate over half the plane is what we're going to do. And this is the result that we get with the edge. This is interesting that on the shadow side, it tails off to 0, but a little bit of light sneaks in if you're a little bit to the left, you know, over here. And then if you look at the right where there's light, actually it will do some oscillation until you get sufficiently far away where then this will settle down. So let's do that. Let's do it. And that would mean here for the integral, we have a naught over 2, and we're going to integrate here from, well, if you want, I can give you the general setup first before we apply the, do the application. So here is our general setup in the 2 dimensions. And what we're going to do is integrate, in this case, the v will go from minus infinity to plus infinity, but the u will go from 0 to infinity. That's where the aperture is, because you're blocked here. And that's going to get you to resolve this point. That's the reference here that we're doing. Then we'll do the other points later. So this is then 0 to infinity for the u1. And then the v1 goes from minus infinity to plus infinity. And that one is the 1 plus I we already have looked at. And if you want to do 0 to infinity, if you come back over here, that's going to be from the middle. That's the 0 where u is 0 to there. So that's going to be 1/2 by 1/2. So that one there is 1 plus I over 2. All right, it's 1/2 on each dimension. Well, this was 1, 1. This is going to be 1/2. So there are the integrals. You know, here's a more detailed picture to show us again that if we go from 0, and this is your u. Remember, this is your u parameter that snakes around there, the spiral. So from 0 to infinity, we integrate that, you got 1/2 and 1/2. So 1/2 plus 1/2 I. It's just simply 1/2 of the result we had earlier. We went from minus infinity to plus infinity, where then you would have a 1 and an I. So if we do that, then for EP, we have a naught over 2, 1 plus I over 2, and 1 plus I. Then if we take the modulus, we can now do the individual, modulus individually each. So this would be radical 2 over 2, because remember 1 plus I modulus square root of 2. And then this would be square root of 2. So when you look at this, you find that these 2 square roots will kill that, and you're left with a naught over 2. And that says that the amplitude is 1/2 the amplitude of the unobstructed beam, which is interesting. But, when you square this thing for the irradiance, you get 1/4. All right. So the irradiance, remember the irradiance of the unobstructed beam is, we had this earlier, is this 1/2 a naught squared. So when you do with the half plane being blocked, it's 1/2 times this thing squared. So since the amplitude had been reduced by 2, this is going to get you 1/4. See, this will be 1/4. And here, it's sometimes just easier to look at the amplitudes and not even put this 1/2 in, since this 1/2 is going to be everywhere, and the physics isn't in that 1/4. See, it's 1/4 of what the a naught squared over 2 is. Say this is 1/4 of 1/2 a naught squared, and this is your I naught. So we can just look at the amplitude, and if we see the amplitude of the unobstructed 1 over 2, we just know it's 1/4 without even doing all this stuff. So that's 0.25, and here we have a plot of the Fresnel diffraction, and at 0 here, if you come up here, this is a little bit above, 0.2. There's 0.4. This is 1 is the unobstructed beam, and it's going to overshoot that. We'll get to that in a second. But I just want to show you that we got here the 0.25. We got that result. Okay, so then here's a nice picture, simulated picture of what the diffraction pattern would look like, you see, where these ripples are simply these bands that are getting dimmer and dimmer and will become a smooth, irradiance after you go far enough to the right. And if you go to the left, notice there's a little bit of light in the shadow region, but then if you get into the shadow region enough, it doesn't take much that you're going to have a darkness. All right? It's just some nice work done at the Rochester Institute of Technology, Professor Michael Richmond, and working with imaging sciences, Professor Roger Easton. So we would like to go after this point. Let's see if we can understand this point. This is the first maximum. So for that case, what we do is, if we're going to be we move over to this point. So now, in this case, the origin has moved over. So we're going to integrate now a little bit to the left from where our perspective is. See, before we were lined up with that edge there, and we integrated from 0 to infinity. But here, being a little bit shifted to the right, we're going to integrate from some negative u out to infinity. And the question is, what negative u should we pick? All right, that's going to be the question. So before we go on to do that, I just want to point out that here, we're always going to have this piece here, and I don't want to have to do that again. So in this analysis, the EP would be a naught over 2, and then I'll integrate here u1, u2, keep that general, I pi u squared over 2 du. And this here, when I take the modulus, I'm going to get a square root of 2. So I'm going to put the square root of 2 in there, and then that's going to kill a square root of 2. And when I do that, I'll have this sort of a general formula with the one-dimensional integration, which will be useful. And here, I don't want to keep the imaginary number because I'm going to do the modulus anyway, and it's going to go away. It's going to be that square root of 2 that's going to be squared. So this is a good, nice little formula, a cute formula that we can apply, see, to the various points. We can apply that to the various points along here, where the integration in the v direction is always going to be the infinity case. So there we go. We got that nice. So we can look at these with the Corneal Spiral, but also they have here, here I have some for you from u being -5 to u to +5 here. These are the results, say, of the Fresnel integrals to, got 4 significant figures here, and you can find more on the internet to like 9, 10 significant figures. In fact, I'm encouraging you to look at that source in a homework problem that you'll be doing. Okay, so I want to find out here, where this maximum is, this first maximum. Here's the Corneal spiral. And I know I want to integrate that u to plus infinity. But now I want to integrate starting with some negative value because I'm no longer lined up, with the edge. And here I look for this long vector. See, if I move it over to here, I'll have this length. But then here I'll have a longer length and a longer length. And I say, whoa, right in there is like the first max, because see, if I come over here, the length is going to be shorter. So there it is. That's going to be the case where the values are, close to a minus 0.7. Now along this line, they're going to be equal, all right? That's like the y equals x line. Horizontal axis and vertical axis, the coordinates coincide there. So here, we're going to try the minus 7. Now remember, when you do this kind of an integral, here I'm going to pick this to be infinity. But remember the way this works, the Corneal spiral and the Fresnel integral tables give you the result. This is c at infinity. Remember, you write this is going to be cu plus isu, and you evaluate at the limits, which is going to be here at some u1 to infinity. So in general, if you're going to go to infinity, this will be the c at infinity minus the c for u, and this is the u where u is infinity and infinity, and that would be at that point on the Corneal spiral. So if you take u and go to infinity, you wrap that u around, and not showing everything there, but it would be at that point there. That's going to be your point where u is infinity, and then this would be going to be plus I with the s infinity minus the s of u1. So here, from the analysis we just looked at, this is essentially going to be a 0.7. That was actually a negative 0.7, and this was a negative 0.7, and this is 0.5, and this is 0.5. So just to make sure we understand that. Here at infinity, the c and the s are 0.5s. But here at u1, which is going to be down in here, where we're integrating from, that is going to have the c and the s is going to be negative and negative 0.7 and negative 0.7. So when we do that, this will become 1.2, and this is, again, 1.2. So you're going to have 1.2, 1 plus I, and here you're going to have your A naught over square root of 2. That still stays there. And then when you go to do the modulus, we're going to have A naught over the square root of 2, and here the modulus would be the 1.2 would stay there, and you would pick up a square root of 2, do that part. This would cancel, and now to get my irradiance for that point PC, I'm going to basically want to work with this squared, but what is 1.2 squared? Well, 12 squared is 144, so that's like a 1.4, and that's going to have you're going to have your A naught, squared, and remember we said you just compare, you just look at that, and that's telling you what's happening compared to the unobstructed beam, all right? I mean, if you want to put in here the 1/2 for the irradiance, that's fine, and it'll be a half here, but then when you combine it with this, that's your unobstructed beam. So really, this is what I want. I want this 1.4. And if you look at this peak, guess what? 1.4. Amazing. So let's now go after this one. That's like the first minimum. Okay, now nice thing about this general formula that we had here, we have the A naught over the square root of 2, and we're going to go from some u1 to infinity, v di pi u squared over 2 du. And now we want to know where the u1 will be to get this minimum. All right, we want to get this minimum there. Okay, so here's what we're going to do. Let's go look at the picture in the book where we have the nice screen here. And we want to move ourselves over some more. So now the P, when we line up that P to the new origin as we're moving it over, we have to integrate more to the left and then go out to infinity. And where would that minimum be? Well, we go to our Corneal spiral. And the Corneal spiral, remember we were at here before, at this U, showing that max, but then if I come on here, I have a minimum, see? Because it's going to get bigger again, see, bigger, bigger, and bigger. And you can see it, the ripples. It's going to get then a secondary maximum, and then a secondary minimum, bam, bam, like that. And they're going to get, ripples are going to get smaller and smaller. So you can actually see this occurring. So we want this one. Well, this one is very close. That's for this, this minimum here. This one is very close to 0.4, negative 0.4 and negative 0.4, all right? So if we look at that and do the same sort of thing, well, it's kind of just, this integral is just actually quite easy to do if you just remember you want this length. This length is the modulus. So let's not put in values and subtract. Let's just look at this, or subtract it kind of in our head. If this is 0.5, and this is on the left side a 0.4, to get here, there we go, 0.4, see? So you're basically looking at 0.5 plus a 0.4. So really to go from here to here, see, this is 0.5 on the horizontal. This is negative 0.4. So here's your 0. So you can think of going 1, 2, 3, that's 0.4. 1, 2, 3, 4, 5, 0.5. So this is going to be 0.9. This is 0.9. And since this is along that y equals x kind of idea, this is 0.9 also. So in other words, this is going to be the square root of 2 times 0.9, because you're looking at a triangle where you have the 0.9 and the 0.9, and you just throw in that square root of 2, 0.9 to get your hypotenuse. So the square root of 2's cancel. So really what I'm after is this 0.9 squared, and that's going to be 0.81, and that's going to be compared to the unobstructed beam, like that's going to be it. So if we come back over to here and look at this and go over there, guess what? 0.8, like we got it, because this is relative to the unobstructed beam. Well, I can't resist. I want to do one more. All right. So if we want to do one more, then we come over here and we want to, here's where we were, and we're going to now go along, we're going to go along U. So U has to increase the spiral, and then boom, down there is the next one. See, that's your next max. Then your next min would be there, and then max min. So we started out with the first max being down here. And then we increased U to get the first min. And now we're going to increase U to get the first max. And that is very close to negative 0.6, negative 0.6. So since we have here the negative 0.6, negative 0.6, we do the same thing we did earlier. We just go ahead and draw a line like out here and then up to there like this. There's a right triangle. So remember from the middle on out, 0.1, 0.2, 0.3, 0.4, 0.5. There's your 0.5. And then here, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So really you want 0.6 plus 0.5. So you want 1.1, 1.1, and that means this thing is a square root of 2, 1.1. And that means we have a naught over the square root of 2, 1.1. These will cancel. And when we do the square, 11 squared is 121. So that's like a 1.2. And then if we come up here to find this and go over there, it's a 1.2. See? And you know, there's the U. If you want to know what the U, well, actually, they've converted the U. They've converted the U back to like the other coordinates, like the X coordinate, the little X. There's a little X coordinate, and there's like the capital X coordinate. And here I want to emphasize the nature of the graph rather than that specifics. I will do one for you though when we apply to astronomy. We will do one of those. Look at real coordinates, and we probably should call this by a new heading, and we're going to do an astrophysics, an example, and this is going to be fringe effects, Fresnel fringe effects during a lunar occultation where the limb of the moon is going to block a star. And we're going to get something like this. All right. In fact, this website I went to, the Rochester Institute of Technology, they were analyzing light passing at the limb of the moon. Right. So in this case, we're going to have to deal with these coordinates, because see, this is capital X. We got to deal with this now. So to do that, let's look at, first of all, this X. And this is where, you know, it is tricky because remember, this X here is the X from the origin. Here, the origin's at this point, in this case, is O is here. So the little x runs this way, but also little u runs that way. And they're related by the formula we had earlier, say, like that. But now if you want to relate the little x here to the big X, that's easy to do. This capital X was the displacement from our original point over here, which was lined up with that edge, to go to the right to find that first maximum. But that big X here, this big X here, can be related to this little x in here. And that this absolute magnitude, to say, of that x is going to be, and I use absolute magnitude because on this side, it's to the left, actually is going to be a negative. All right. So here, and that's because we move this point P is aligned with the origin. All right, so if you look at those triangles, you'll have the absolute value of the x1 in here over rho naught. That's going to be the big X, and this big X over here is positive, over the big length, rho naught plus r naught. So here is one triangle, and then here is the bigger triangle. So that'll give you the big X, which is what we're after. It'll be rho plus r, naught over rho naught times the little x. And then here, in the limit, since the star is going to be very far away, we're going to take this to be infinity, and this is going to become the moon in a second. So if we do that, limit, as rho naught goes off to infinity, then here, well, you can see this is going to be 1 plus r naught over rho naught. If you run rho naught to infinity, you're just going to have 1. So in other words, the x, big X, is going to be equal to the absolute value of the little x. Nice. But now let's look more carefully at this u, which we have from earlier in the course, where we're copying this down from before. This is the coordinate transformation to make the Fresnel integrals look very nice. So now if rho goes off to infinity, you can see that what will happen here is that if you do the same trick, divide top and bottom by the rho naught, or in fact, just divide the rho naught into rho naught to get 1, divide the rho naught into r naught to get this. This is gonna go away when you go to infinity with the rho naught. So you're gonna have this. You're basically gonna have, this is gonna be gone, this is gonna be gone, because you're gonna have, this is gonna just be 1 over r naught. So the u is gonna be x times the square root of 2 over lambda r naught. Now we bring the moon into the picture. So see, here is the star, and we're a little bit to the right, so we're no longer lined up directly with that limb, so you integrate, from the left a little bit, and we're going to go after the first maximum. That's what we're looking for, the first maximum. But we know the first maximum from the Corneal spiral was down here. So we did that problem already, down here to find that length with the point, remember the 0.7, and that we worked that out, we got the first maximum, but now we need to know what u is. But see, this is the u along this, and it's between 1.0 and 1.5, so each of these little notches or little dots is a 0.1, 2, 3, 4, 5, this is negative, 6, 7, 8, 9, 10, 11, 12. So it's like a negative 1.3, we'll say 1.3. Looks like it's a little bit closer to this dot than that dot. But here's where you can use the tables, if you want it to be more accurate. You can look up in the tables rather than make an approximation here. But this is good enough for us. So the u is going to be the 1.3. All right. So now we use this formula. This is 1.3. We don't know what the x is. That's going to be what we're measuring because that's at the screen. Remember, the little x and the big X are going to be the same because that star is far away. We already looked at that. So you need the square root of 2 over the wavelength, and we'll use the wavelength of 500 times 10 to the minus 9 meters. And the R naught is the R naught here. If you come back to this picture, R naught, and that's the moon, R naught is the distance of the moon. So like how far is the moon? So when we do that, I think I'd rather take this equation though and solve for x first. So x is u, then the lambda R naught pops upstairs and you get this. So you flip this and take it to the other side. I'd rather work with this because that's what I'm after. I'm after the x. So here, this is the 1.3. And then here, now I'm ready for the wavelength, 500 times 10 to the minus 9th meters. And then I look up the distance to the moon. It's 380,000 kilometers, or 240,000 miles. So that's 3.81235. So that's 3.8 times 10 to the 5th, but that's kilometers. So really this needs to be 8. So I can put in meters. And then I divide by 2, and then this is to the 1/2 power because of the square root sign. So when we do this and work out the mathematics on this with the calculator, I could show you an intermediate step here, and this is the big X or the little x is 1.3. Here is going to be 500. I like to do some work with the exponents. 10 to the minus 9th, 10 to the 8th is 10 to the minus 1. And then there's going to be a 3.8 floating around over 2, 1/2 power. And then here, this is going to be 50. you know, when you take 500 and multiply by 1/10. So you have 1.3, you have 50 times 3.8 over 2 to the 1/2 power, and then you're going to get 12.7 meters. That is awesome, all right? So that means here, if you look at, you see here's your 0, your origin, here is your, you know, your big X is going this way, and then this peak, this is the graph I got from the professors. See, look, this 12 at 13. It's like 12 or 13. It's like, look, this is 10, and this is 20. So like we got it. Like this is like real. This is meters. Like we're talking 13 meters. This is like on Earth, actually making a measurement. So that is a very, very nice, connection. And I wanted to do one connection with the real laboratory kind of distance, because that U, or those rich in physics and can get these max and min in the laboratory, just gets you an actual distance. But we're not finished. Let me go back to W, make this W3. What about the shadow region? What about this cool little tail that's going down there like that? Yeah, what about this tail? Like, look at that. There's no oscillations here. Can the Corneal spiral predict that? Well, let's go ahead and see. So if we look at the tail, what we want to do now is move, see, line up. So origin is now going to be in the shadow region. So we want to integrate here from some plus U to infinity, because we're always integrating over the aperture part. So since we're lined up here behind where the shadow is, we're gonna, this adds the U, and this U is greater than 0 now. This U is greater than 0. So, because we're back here, if that's the origin, then this extra piece U is greater than 0, and then here's from 0 to infinity. So, if we want to do that, if we integrate it from 0 to infinity, we would have the half plane integration, but now we're going to integrate with the positive U. So if we do that, like here, it's dimmer. This has become shorter. And look here, dimmer, 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 dimmer. There's no oscillations. It's just getting dimmer, dimmer, dimmer. And that explains the tail. This tail has been explained, see, by those integrations. And then eventually, you're going to get the 0. When you're in that shadow region, you're 0. It's like dark. All right. So on the extremes, in the shadow region, you'll be dark down here, dark, and then here you'll have 1. You'll have the unobstructed beam. You're in the light. You're far away from the edge. So this is going to be unobstructed beam. That is really neat to see those extremes on either side. Unobstructed beam when you're way out there in the lit region. And that would be, if you come over to this diagram, that's like way out here. If you get way out there, well, that's where it's all light. Like there is no obstacle. Like you're way out there. So way out here, you're going to have then the unobstructed irradiance, so like a 1. And then if you go out to the left, 0, like you're in the dark. So a lot of rich physics, Fresnel, diffraction. Now W4, the Fresnel single slit. Now we can look at the single slit as having 2 edges come together. Now this is what we found when we had, say, everything like blocked off here, and there was an opening here, half the plane, like with the moon. We had this, But if we have another like blocked area and then bring these two together, then this is the slit, like this is the opening. So when you do that, get closer and closer, you get all kinds of neat effects. All kinds of stuff can happen here. So what you're doing though, in this case, is if you go back to your master formula, we're still going to integrate from minus infinity to plus infinity on the vertical. But now U1 and U2, see, we'll be looking at the extremes for the slit. So this is the diagram to help us understand that. We have here a wall, and we have here a wall, goes off to infinity, and then we have the opening. So we then integrate over the opening. So we're going to go from a U1 to a U2. And what's very interesting about this is that U2 minus U1 will always be a constant. It will be the width of the slit. And remember, when we move to other points along here and our origin moves with us, we go from some other U1 to U2, but the key will be is that the difference will always be B. So I drew a diagram here to help you see this even better. And what this diagram is doing is saying, okay, if we're in the middle here, we're going to integrate from minus B over 2, this is the U1, minus B over 2, to U2 is going to be plus B over 2. Nice. But if we then are going to shift to another point down here, let's say to the right, then when our origin moves, we're going to be going here for a different U to a different U, but the difference will still be B. So what we can do is say, let's take the middle point here, say being some U of P. So if that middle point is U of P, we want to integrate from U of P minus B over 2 to U of P plus B over 2. And then as we move farther and farther away, the starting point here will be, greater as we move this way. That is going to increase, but the interval will be the same. So the way to visualize that in the Corneal spiral, if we were lined up in the center, we would go from minus B over 2 to plus B over 2. And this U, when I use B, I'm using B in the U coordinate B. You'd have to translate back to get the actual width. All right, so there you go. And then if we are going to start a little more say more negative, like down there, we would then go still the same. The difference would have to be the same, because when you take the U2 and minus the U1, you have to get the width of the slit. So if this is the width of the slit in U coordinates, then this has to be the same string length. B has to be the same string length. And here, same string length. But now, as we do these, we basically get all the values by snaking around. Just imagine that string, then here is a little bit later it's there, then here, then there, then there, and snake around. And when you do that, you get the effect. Here is a video from many, many years ago, a film loop, and to illustrate this, this goes way back. Check this out. And I call that snaking around. And there's a baby snake found in my basement years ago. So when you do that, and you get all kinds of neat effects, Mathematica is going to do it for us. And when Mathematica takes care of us, look at this beautiful case. And here the Mathematics has calculated the actual slit width and the light that you're using and how far you're away from the slit, your screen. But I just want to here show you the different pictures that you can get. And then here for a slit width that's larger, look at that. And then down here for even larger 0.19 millimeter, look at that. And your screen's 1 meter away in these cases. So look at that. You don't get the same there. Let's see. You have here 2 peaks, and like in the middle, it's the minimum. And here, look at that, 0.25. You got this. And then here, with 0.59, I got this from the Mathematica website. Marvelous website, doing all this stuff. Look, you get this. And then here, with 0.67, and doesn't this look like we're bringing in 2 edges? See, here's the edge effect that we did. Here's an edge effect, and bringing those in, see, you get this. You bring them in closer, you get this. You bring them in even closer, you get that. And bring these in closer, you get this. You bring them in very close, and look, if you get these big peaks getting very, very close, you get the one big peak in the middle. Amazing. And you're gonna really get to understand this in a cool way, because I'm gonna ask you to do one of them for homework, and that'll be your only homework assignment. It'll be broken up into 2 parts to do one case, to get one of these, and you'll be using the Fresnel integral tables, and I encourage you to use a spreadsheet, and I'll guide you through how to set up the spreadsheet by cutting and pasting.